Oh, yeah. Our next presenter is, can you hear me? So, our next presenter is Gundy-Burlet, who's going to talk about LADEE.
Awesome. I think I'll use this mic. Okay, so I'm going to talk about infrastructure and process improvement after LADEE. I'd like to recognize my current team. We've reformed ourselves as the Common Avionics and Software Technologies Group, and these guys are doing great work in rebuilding the infrastructure after LADEE. So a roadmap here, a little overview of the software, and then I'm going to indulge myself and give you some of the mission highlights from LADEE. We did a bunch of cool stuff. And then after that, I'll talk about the process improvements that we're working through. So for those of you who don't know about LADEE, it was the Lunar Atmosphere and Dust Environment Explorer, and it was designed to examine the lunar dust environment, and it was looking at the composition and variability of the dust atmosphere around the moon. So it was launched on September 6th of 2013, and we had a planned impact with the moon on April 18th of 2014. So last year when I gave this presentation, it was on lessons learned. It was right in the middle of the mission. So we were a enhanced Class D mission with Class B flight software. The software was provided by Ames and Goddard, and basically so was the spacecraft. We built it in-house. We had several science instruments on board the spacecraft. We had a neutral mass spectrometer, an ultraviolet spectrometer, and a lunar dust experiment. And think of the lunar dust experiment as like a bug zapper out in front sweeping dust out of the atmosphere. It's kind of cool. We had one technology payload. We had hosted a lunar laser communications demo, which was extremely successful. Another first for LADEE was that we were the first spacecraft to launch on a Minotaur 5, and we launched out of the Wallops Flight Facility. So in terms of the flight software, the scope of the avionics group at Ames was to develop the onboard flight software. We also, which was the Class B flight software, and we also developed the support software and all of the simulators to test the flight software. And also those simulators went forward, and turns out they were used in INT and mission operations for training and validation and verification, which Nathan Benz is going to be talking about in his talk. We also were responsible for the integration of the flight software with the avionics, and being a good NASA mission, we followed all of the requirements of NPR 7150.2. Which part of that was requiring that you be CMMI Level 2 or equivalent. We were certified CMMI Level 2 during the mission, and were recertified at the end of the mission. We also used the NASA Software Assurance Standards for LADEE. This was a model-based development effort where we used Simulink as the modeling environment, auto-coded out the flight software, auto-coded out a simulation of the spacecraft separately, and developed the flight software using 5 incremental builds. And of those 5 incremental builds, build 4 and the build 5.x's were released to the spacecraft. Build 4 was an INT release, and build 5 was for the spacecraft. And of course, we are one of the groups that uses CFE. Back when we froze our software, we were on CFE 5.2, and I don't know which version of CFS, and of course OSAL, and we used ITOS just like the previous speaker did. We were on broad reach RAD 750, so we had broad reach drivers. We had fixed on VxWorks 6.8, and when we froze, we were using MathWorks 2010B and some of the associated toolboxes with it. So what I'm saying here is take a look at this spacecraft, extremely successful. All of our components, the tool chain was frozen in 2011. So the tool chain itself is old by today's standards. But we were developing software in it, in that tool chain right up until the final release to the spacecraft. So this is your standard lollipop diagram for CFE type effort. So everything above the software bus line here is a Simulink application. So each one of them was auto-coded out separately, and we have an automated process for auto-coding out these applications. We have a Simulink interface layer that provides the proper CFE wrappers for communicating on the software bus, and also gives us table services. So these applications are controlled just like any of the other CF applications on the bus. The blue bubbles here are the standard CFS applications that we used, and the green bubbles were the hand-developed items on the spacecraft. And of these, probably most of the hand-developed software was in the hardware I/O, talking to all of our hardware systems. And Doug Foreman will be talking about that on the final day. So, of course, that's all layered on the system support and OS services, and so typical CFE diagram. Okay, so now I'm going to get into the fun stuff. This is, Gene Cernan, when he was orbiting the moon, he noticed that as you came across the terminator, that there would be this beautiful flash, and there were rays coming out from the line of the terminator, and you can see those pictures on the far right there. And Clementine noticed a similar sort of thing with sort of a glow as the sun started coming over the surface. And on LADEE, what we did, we didn't have a camera on board LADEE, except we had the star tracker. And so what you're seeing here on the left is a series of star tracker images as we taking snapshots of the moon's surface as we're progressing across the moon's surface. And as the image recycles, you'll see the Pleiades jumping up, going up from the corner to the right. And here, when you get right before you can see the same sort of picture that what Gene Cernan found in his diagram. So we never were able to snap exactly the second, the instant in time where we could mimic one of those pictures. But this is very indicative of the sort of thing that Cernan saw when he was on the spacecraft. And if you go out to the LADEE website, there's all sorts of other great star tracker pictures of the moon's surface. So this picture here it's stunning to me that the Lunar Reconnaissance Orbiter was able to take a picture of us in flight. And so they were on a mostly polar orbit. We were on a mostly equatorial orbit, and with both spacecraft traveling at 1.6 kilometers per second, they were able to snap a picture of us. And so you can see in this fadeaway, I'm gonna walk around and point.
You can use the mouse.
I can use the mouse. It didn't seem to pop up. Well, all right. So while there's okay, I see it. There are very few pixels. You can actually see a couple of pixels indicating the star tracker hanging off the top here. You can see the bell of the main engine, and so you get a glimpse of the different orientations of the different solar panels. But this is just stunning to me that LRO was able to capture us this way. Okay, so now I'm going to talk about the final day. So this is April 18th. A lot of us on the flight software team were also working on mission operations, and I was fortunate enough to be on console that day. So let's see if I can get this to... So we decided we would name the possible impacts like you would name one of the major storms that generally hits the East Coast. And so we were careful not to pick any names of any of the team members. So these are, so we had Andrea, Bruce, Charlene, Derek, Aaron, and Francis. And there's actually two sets of lines on each of those lowest height above terrain. One is the Lunar Prospector data, and then the other one is Gravity Probe B data. And unfortunately, we'd started out the mission not having gotten the Gravity Probe B data, so so we were using the lunar prospector data as our baseline, and you can see that, you know, where it's thickest, that's where the lunar prospector data, and it's very typically higher than the gravity probe B data. And so we were propagating out, and all of a sudden we noticed that the gravity probe B data was predicting potential impacts with the surface. And so if you take a look at this, so Andrea was our first one where if it was below 2 kilometers above the moon's surface, that was when we started to really get antsy about possibly hitting the moon's surface. 2 kilometers, that's screaming, by the way. So Andrea was only 1.44 kilometers. And so you go around the moon, and then 2 hours later, you're coming around again. So 2 hours later, 1.23 kilometers. And this was Sundaram crater that was giving us conniption fits. And Charlene was 0.88 kilometers. Derek, we got a little bit of respite with 0.94 kilometers. And you can see how close these are on the gravity probe B data. Aaron was 0.29 kilometers. We're all going on that one. And then Francis, we hit. So we hit just within view as we were coming around the moon. So here is Lunar Reconnaissance Orbiter once again coming to our, I'm going to back up on that. And so they were able to take an image of our final impact zone, and you can see the impact, doesn't like me. My computer will cycle on that infinitely. Okay. All right. Okay, I am not getting this easily. Told you guys you should have let me use my own computer. Okay. Okay, there we go. So you can see the nice little spatter zone from the Lunar Reconnaissance Orbiter imaging. Okay. Okay, so the final status for LADEE, for the flight software team, we used all of the capabilities of CFE on this mission. We had regular table updates of various applications. We were always updating absolute and real-time sequences. We had fault management updates. We made lots of updates to the thermal system because the moon's environment was significantly more thermally challenging than what we thought about. And we actually did some updates for defect reduction. In particular, that Star Trekker, who joyously gave us all those images, also gave us a lot of trouble whenever it got close to the moon's, whenever it got close to looking at either the moon or the Earth, it just took one look at a big bright object and went, oh, I'm going to delay my quaternion estimate for you. So we had to patch our state estimation system in order to ignore those delayed quaternions and errors in the quaternion returned when we were getting close to the big bright object. So we also had one unanticipated reboot. We were running the laser communications device, and just when we finished sending down one of our SD-RAM partitions, what you had to do to make it, to fill up its queue was send down whole SD-RAM partitions. There's an interrupt at the end of that, send, and inadvertently we had a task lock in the middle of an interrupt service layer. Very, very difficult to find. Our V&V system didn't find it. Our inspection system didn't find it. But of course, the LaserCom found it. We actually had an opportunity. We had an extended mission where we got permission to go for another month after our scheduled end date for the mission. And that additional month of time included time for engineering experiments, and it also included an eclipse. So we had an extended eclipse that was expected to actually kill the spacecraft. As it turned out, to make it through that eclipse, we had found a defect in our battery control system software. And so in order to get through the eclipse, We at least had to upload new battery control software, but we also were able to fix the interrupt handling for that unanticipated reboot. And so they gave us the opportunity to upload a whole new image of the flight software. We did, rebooted into it, and we had approximately a month's continuous operation on that new load without any defects found during that time. And so the team was also recertified for CMMI Level 2 in May of 2013, so it was right in the middle of all the final flight software load. It was really impressive having to do all that together. So in terms of the mission, I'm going to say a successful deorbit. I mean, there's no other way. You couldn't escape the moon's gravity with the power we had on board, so we deorbited well away from all of the Apollo sites, and that was successful. Our lowest science operations were actually conducted under 2 kilometers over the moon's surface. Our final pass, it was really awesome because our flight director we finished our data taking, and he had a very short, like 2 minutes of time in order to download all of the spacecraft data from those instruments, and all of the housekeeping data off of the spacecraft. And it was like 10 seconds to go before the potential impact, and it was like, got it. So, I mean, it was one of these, Howard being a cowboy, but it was awesome. The laser communications demonstration was amazing. 622 megabits per second downlink rate. I wish I had that at my house. I keep offering to have a laser communications terminal in my backyard, but nobody takes me up on it. As I said, we survived an eclipse. The only thing we lost was a pressure transducer, and we were able to work around that. So it was a spectacular engineering experiment and showed where the thermal modeling could perhaps be performed better for the next spacecraft. So basically, on a planned 100-day mission, we had 188 days of lunar orbit with approximately 200% of our planned science data returned to the Earth, and all of the science goals were met. Okay, so, all right, spacecraft's gone. What do we do now? So we took a look at several of the New START efforts at Ames, and a lot of them will look at CFE and go, oh my God, that's so complicated. I'm just not going to, there's too much special knowledge and it's too heavyweight. We're just not going to even try it. And part of it is extremely well documented, but it's such extensive documentation, it's hard to know where to start sometimes. And you do need somebody who has some experience consulting. And a lot of people have very unrealistic budget schedule and other expectations. Ames is do it really dirty and cheap, and anyway, we're trying to educate them, but it's difficult. So our current effort is to do what we heard in the panel session. We're trying to do a similar thing, where we're trying to form a core avionics group that produces a software product line that can be put out to very small spacecraft missions and larger CubeSat missions. And what I'm talking about is on order of a 6U CubeSat. We've got several examples of those at Ames in planning phase right now. So our software architecture is based on LADEE, but with all of those core components updated to the modern standard. So OSAL, based on the open source version. Same thing with CFE. I know Goddard is going crazy trying to get CFS open sourced, and we are awaiting that version. We're at VxWorks 6.9. We've got MATLAB and Simulink 2014A, and we're adding additional RTOSes. So we've got a Linux version that we're operating on, and we're also going to be incorporating RTEMS. So what we're trying to do is create a flexible software and avionics line for smaller spacecraft missions with, a set. And what we're going to try to do is say, okay, if this is your sort of mission, we recommend this matrix this is the performance that we recommend for you. So we've got several processors that we're targeting. We're running right now on a BeagleBone Black. We're looking at the Zinc. Of course, we got our PowerPC. That's what we did for LADEE. And we're also looking at the Leon processors. One of the things that a lot of lessons learned through LADEE, particularly where we're getting into a distributed development environment, we're changing our configuration management from Git from Subversion. The previous speaker had some very good comments on why one would want to do that. We're also moving from Track and the associated wiki to Confluence and Jira. We became familiar with that within our mission operations, and it's very flexible for us. And what's nice is it's in the same family of tools as Atlassian's Bamboo, and so we've got a continuous test going right now with Bamboo integrated with our Jira ticket system. So anytime anybody makes an update into Git and it's in the right format, the Bamboo automated test runs and tells us whether or not that is compliant with our unit test suite. So we're also trying to develop a set of NPR 7152 plan templates that make it just easy for the next spacecraft to pick it up and do it. We've got an extensive test suite. What's really cool about the CFS working group is that, of course, we've got all of the CFE, CFS unit tests that Goddard has supplied, but Johnson has got an even more extensive test suite. So we're working on incorporating all of those and making them available to the CFS community. And then we'll be continuing on with our peer review and formal inspection programs that we've got. So in terms of collaborations, we are in the process of trying to follow in Goddard's footsteps, and we're trying to open source our Simulink interface layer for CFE, CFS. It's currently available with a software usage agreement, and I'm fighting with the lawyers to actually make it open source. You would think that the component CFE is open source and Simulink is a commercial product. Why wouldn't this little chunk in the middle be open source? But anyway, it's my goal in life to win this battle. So right now, I say here it's currently consistent with 6.3.2. I found out on Friday that it's actually currently consistent with 6.4.0, and we will continue to update it to make sure that it is consistent with the open source version of, and test it with the open source version of CFS when Goddard is able to release it. As I say, no firm date, but I will win. We are participating in the CFS working group, and that I love the community. When we got together, everyone was in the sharing mood, and that is just something I want to make sure we continue. Really, at the end of this, what we're doing is proposing this new software in avionics space as a core for many of the upcoming missions. In particular, Resource Prospector is using this product line. There are various CubeSats, including BioSentinel, and some of the propulsion pathfinders are considering using this. And there's also planning for LADEE follow-ons. Now, let me see. I've got one more fun thing here I want to show. Okay, so this is a video taken from STK of the final orbit of LADEE. You can see the Earth back in the position there from where we're looking at LADEE coming over the horizon. You can see we're just screaming along the moon's surface here. You know, the local surface was quite mountainous in this area where we crashed. And that's the position we were in the orbit. And so here's Sundaram crater coming up. And that was just in view. Okay. Anyway, thank you very much.
Questions? Yes.
So a common theme today has been moving from Subversion to Git, which I'm very interested to hear about. So, because I've had a lot of experience with Subversion, and I'm curious to hear about Git. Do the developers prefer it? How easy was it to train them? Is it good for parallel development? You know, whatever you can talk to.
So in terms of if you're focused on parallel development at widely diverse sites, Git is the way to go. It's much, much easier to pull information from somebody else's branch and incorporate it in your branch. You have a lot of control what you pull in. One of the problems with Git is that it really imposes a completely different workflow on you. And a completely different structure to your flight software. For instance, we've re-architected, and so have most of the other CFE projects who are also working in Git, so there was another reason for it. But it's now, we have a very, very flat architecture for the overall software components so that we can, each component is its own Git repository that we can pull and synchronize with other people. I'm a long-term Subversion person, and I've been working in Git for a couple of years, and I'm still not completely confident in the workflow. There's way too many options. Your group has to really define how you do your workflow and recommend what your best practices are for your particular group. But that being said, my developers are rabid about Git. So, yeah.
Can you say a little bit more, elaborate on defect reduction? What process do you go through to?
So we had a, I'll refer you to my last two flight software talks, but we had a unit test suite, we had integrated test suites, we had scenarios of all the major phases of flight, we had scenarios for all of our fault management activities, and these all got run. And the data was put into a very large database, and then we had a script that would post-process all of this data to look for violations of our requirements. And that was at the level 5s and below, and we also had a separate report for the level 4s. It would generate information such as provide all the bidirectional traceability between the requirements, the models, the code, the test suite, and what the results were. And it would tell you why you passed, not just that you passed. Or all automated. It was actually automated using Simulink Report Generator. It was very, very easy to do to program under Simulink Report Generator and have it execute test scripts within our LADEE hierarchy that were operating both on the Simulink models and on telemetry data that we had pulled down through our full flight-like interfaces using ITOS.
You know, it's worth mentioning that you were designing the test cases long before there was software.
Oh, absolutely, because the nice thing is once you've got the requirements and you have the software design, then you can write the test case before your developers are even doing it. So it was nice. We had this suite mostly developed, and then as the developers were coming in with their new software, with their new builds, I could say, fail, go back.
How large was your software team, and how did you juggle getting CMMI Level 2 at the same time getting this project together? And did Ames pay for the CMMI? Because I know it's not cheap, or was that a LADEE expense?
Ames, our software development office did it. You will notice that I have a lot of gray hair. This is the result of both small children and LADEE and CMMI. We had peak team was 14 people. But the CMMI effort largely fell on me, and I was the software quality lead at the beginning of LADEE, and then when our flight software lead went to mission operations, then I took over the flight software position. So he and I basically performed the CMMI. It was many hundreds of hours. Yeah. Yes.
In addition to Xenomai and RTEMS, do you plan to leverage any of the free RTOS work that they're doing at Goddard?
Hey, anything that gets put into that CFE, CFS working group set of repositories, we are looking at. So there's all sorts of great device drivers and RTOSs being shared. There's a lot of, so what was exciting about that is here we are all doing our little development efforts and looking across the agency and seeing, hey, Glenn is doing that way better than we are, and wow, Johnson's got these Leon 3 device drivers that are just awesome. And so we've got our own contribution with the continuous integration Bamboo test suite. So it's just been great being able to look at, survey what's going on around the agency and pull it.
In addition to that, I saw you mentioned CubeSats. Do you plan to get ingrained in, I know Goddard's planning a big, sharing their CubeSat work. Do you guys plan to do kind of the same thing with your CFE work?
So the CFE work we're sharing through the CFE, CFS working group. I wanted to make that a clean, we don't, as far as I'm concerned, we don't own it. We're part of that working group, and it's going to be the working group's decision on how they share it with the outside community. We are working on doing technology invention disclosures for most of the rest of the LADEE software. Some of it will be available under software usage agreements, and others it'll be reimbursable Space Act agreements. So it is, but it's an extensive process, and I don't understand why. I haven't done anything technical since LADEE crashed, let's put it that way. I've been learning lawyerese.
We have time for one more question. Anybody else? You have, hold on, sorry.
I've been away from JPL community, but do you have some sort of like an enterprise working group meeting, sharing lessons learned from different programs or projects and whatnot?
So I have a lessons learned talk from LADEE that I actually gave here last year, and I've given it at software working group meetings within NASA. And the CFS is definitely one of those sharing the lessons learned, sharing knowledge. I think it's a core value. We all need to do it.
With that, it's worth pointing out that all these presentations are at www.flightsoftware.org going back 7 or 8 years. So go
right.
get it there. Okay, thank you.
All right.